My dear students, parents, teachers, and principals of all our council affiliated schools across India and abroad, welcome to this CISCE virtual learning series. It is the council's humble gesture and initiative to reach out to our students through our exclusive YouTube channel using StreamYard. We are in the 6th month of the COVID-19 pandemic, and the crisis does not seem to relent anytime soon. Given that all schools are closed, the Council has decided to proactively involve its students in some teaching learning activity through this initiative. While many schools have been doing excellent work in conducting online classes for its students, yet there are some schools which have not been able to do the same for their students. The Council is concerned about these students, especially those at the ICSE and ISE level. Therefore, the Council has arranged for subject experts for all the major subjects at the ICSE and ISE levels to address students' concerns and to suitably guide them in these subjects. These lessons can be viewed exclusively on the CISCE YouTube channel. I request all our students to be attentive and participate actively in these interactive live lessons. I am confident that our subject experts will be able to assist and motivate each one of you. Lastly, I would like to place on record my most sincere gratitude to Mr. Francis Joseph for coordinating with our research division and examination sections to make this possible. We plan to continue this series for as long as we can so that the Council can reach out to our teaching community in general and to our students in particular. Thank you and happy learning.
Good morning, everyone. Students, teachers, principals, whoever is watching. Now, today we are going to talk about sound. Now, sound is such important part of our life. No communication is possible, direct, face-to-face, without sound. Now, let us see what is there in ICSE syllabus for sound. So, we have reflection of sound waves, echoes, their use, simple numerical problems on echoes. This is the scope given by the Council. Second, natural vibrations, damped vibrations, forced vibrations, and resonance. Special case of forced vibration, that's a resonance. And that's the scope. And loudness, pitch, quality of sound, that is the scope. Now, today we are going to focus on the second module. That is natural vibrations, damped vibrations. Now, it is not possible to build any structure without foundation. So to understand this, let us start with some basic concepts. Now, sound is a form of energy audible within specific range of frequency. You have learned the frequency range, which is 20 Hertz to 20,000 Hertz. Then sound travels in the form of waves and needs a medium to travel. Sound cannot propagate in vacuum. It is a mechanical wave. Why is it called as a mechanical wave? Because it requires material, medium. It travels in solids in the form of transverse waves and liquids and gases in the form of longitudinal waves. Now, to the human, the sound between 20 Hertz to 20,000 Hertz is audible. But that does not mean it is exactly cut off. You will find certain exceptions. We can hear slightly below 20 hertz, slightly above 20,000 hertz. Or within this range also for different age groups, the audibility range is different. Now, human ear is more sensitive to the sound between the frequencies 2000 hertz to 3000 hertz. Now, ultrasonic sound means any sound having frequency more than 20,000 hertz. Infrasonic sound means any frequency less than 20 hertz. Now, in relation to these terms, there are identical terms which I'll be coming to it later on: subsonic and supersonic. Very often students find that ultrasonic is same as supersonic or infrasonic is same as subsonic. But there is difference which I'll come towards it later on. Now, as I told you before, this video will make it clear that for different age group, audibility range is different. In fact, one day when I was teaching in the class, one child had a mobile and he was passing the message to the other. I couldn't hear, but they could hear among themselves because that frequency was audible to only teenagers. So as the age group differs, the frequency range differs. Now, when I'm going to play this video, you will find that the initial sound, in fact, I have cut out this video. I have not taken the lower frequencies to save the time. But as we reach the frequencies around about say 10,000, some of the adults will not be able to hear that sound, but students will be able to hear though because they are younger. So as the frequency proceeds, some of the students may not be able to hear, some of them may be able to hear. So you will come to know that for different age group, the frequency range is different, audibility range is different. I can hear the sound. I think everyone must be hearing this sound. Now the frequency will change faster. Still everyone can hear it. I'm sure all of you must be hearing this sound. Some of you might have stopped hearing this sound. I can still hear the sound. Student must be hearing it. Now even I cannot hear the sound. I'm sure students are hearing it. Some of the students must have stopped hearing it. Some of them may be hearing it. So with this video, I'm sure you must have realized that for different age group, audibility range differs. So 20 hertz to 20,000 hertz is in general for the entire human being. Let us go ahead. Sound, how is the sound produced? Sound is produced due to vibration. Now, if I move my hand in the air, sound is produced, but it may not be heard either because of insufficient frequency, outside the frequency range, audibility range, or there could be insufficient intensity of sound. But any disturbance in the medium produces sound. I've already said that sound requires material medium, but to propagate these properties of the medium are must that the medium should be elastic, without which the particles cannot vibrate. They should have inertia and minimal frictional resistance, because if the frictional resistance is greater, most of the energy will be utilized in overcoming the resistance, and the sound will not be able to propagate further. Now, there are two types of waves, electromagnetic and mechanical. Electromagnetic waves, such as light waves, do not require material medium. They transfer energy. Basically, a wave means through the waves, energy is propagated. So, light transfers energy in the form of electric and magnetic field. So, they do not require material medium. But sound does. Sound travels with approximate speed of 330 meters per second in air, and of course it varies depending upon the conditions, which you have learned in the lower classes. Now, this I was talking about subsonic and supersonic as compared to ultrasonic and infrasonic. Now, supersonic means any speed more than the speed of sound, and subsonic means any speed less than the speed of sound. But ultrasonic means any frequency above 20,000. So when I'm talking about ultrasonic, it is related to frequency. Supersonic is related to the speed of the body. Infrasonic is less than 20 hertz. Subsonic is less than the speed of sound. So students often get confused between these terms. Now, when a wave propagates in a medium, it transfers energy. But what are the characteristics of the motion? Some of the important characteristics are, it travels at a constant rate. That means whatever time it takes to transfer the energy from the first particle to second, second to third, third to fourth, whether the particle is transferring more or less amount of energy, the time taken to transfer the energy will be the same. So that means the wave in a given medium travels at constant rate, its speed remains the same. Now, when a wave propagates, the energy is transferred in forward direction, but every particle vibrate at the same place about their mean position, which I'll explain it to you later on with the help of a simulation. Now, when a wave enters from one medium to another medium, when a wave enters from one medium to another medium, the velocity of the wave changes, but the frequency remains the same. Frequency depends on the source. The velocity changes due to the change in the wavelength. The mechanical waves, in fact, transverse and longitudinal waves in detail you need not know, but as a basic wave motion, you can know that transverse wave, the medium particles vibrate perpendicular to the direction of wave. Longitudinal, medium particles vibrate parallel to the direction of wave. Now, this is a simulation in which you will see how the energy is transferred by a longitudinal wave. Now, this is a longitudinal wave. When this wave propagates, it will appear as if this bunch is moving forward. But if you focus on the first particle, you will come to know that every particle is just vibrating at the same place. Now, this first particle will vibrate to and fro about this dotted line. Just focus on that. So this goes to and fro. It has reached the other extreme position, goes back over here. So this particle doesn't go further, even though the illusion Due to optical illusion, it appears as if the bunch is moving forward. So when a wave propagates, every particle vibrate about their mean position. Now let me open this for my reference in case I have to write anything. I can write it and explain it to you. So I'm opening this file and keep it open. Now the next one is this. You will understand how actually a wave propagates in transverse wave. So in this case, these are the particles carrying the energy. I'm explaining this because with respect to this model, you will understand the definition, time period, frequency, etc. So this is the first particle. When it receives energy, energy is going to be propagated in this direction, but the particles are going to vibrate perpendicularly. So the first particle receives energy. The arrow indicates in which direction the particle is vibrating. As the wave propagates, the next particle receives energy. So it starts vibrating. By that time, this particle has gone further. But when this happens in a rapidly, it appears as if this particle is only moving forward. I'm moving it. So the particle, every particle vibrate about their mean position. This particle had gone up, it has come to this position, now it is coming back to the mean position. So if you see that when this particle has gone to the extreme position, came back over here and again came back over here, by that time the energy has reached to this point. Now with respect to this model, you will understand the definitions. Now with respect to a wave, we always talk about time period. Now, what do you mean by time period? Time taken by a wave particle to complete one vibration. That means when this particle goes to and fro and come back to the mean position, by that time the wave reaches over here. So I can say whatever time the wave takes to complete one vibration, or the time taken to pass one wave through a point, because when the wave reaches over here, the particle completes vibration. I can say the time passed is time period of the wave. Then its SI unit is second. Then second one is frequency, denoted by F. It is a number of vibrations completed by a wave particle in unit time, and its SI unit is hertz. Once again, when this particle completes one vibration, goes to the extreme position, to the other extreme position, back, one wave will be completed. If this particle completes second vibration, from this point onwards, one more wave will be formed. So whatever number of vibrations are completed by the particle, same number of waves are passing through that point. So if I have to define the frequency, I can say the number of vibrations completed by a wave particle in unit time, or the number of waves passing through a single point in the medium in unit time. SI unit is hertz. Then amplitude. It is the maximum positive or negative displacement of a wave particle from its mean position. Its SI unit is meter. So in this case, if I consider the distance from here to here is amplitude, or even it is from here to here, it is amplitude. It is not right from top up to the bottom. Amplitude is from mean position to the extreme position, whether it is positive or negative. Then the next one is wavelength. It is a straight distance between consecutive particles of a wave which are in the same phase. Now, what do you mean by that? Now, if I consider this horizontal line, the red line which I'm drawing, you will find that this particle, this particle, this particle, this particle lies on that line, and their distance from the mean position is same. But this particle is vibrating toward this extreme position, this particle is vibrating towards the other extreme position. So I cannot call these two particles in phase. But the next particle which is over here, it is in phase with this because both of them are at a same distance from the mean position and both of them are vibrating towards the same extreme position. So if I consider the distance from here to here is a wavelength. If I consider the distance from here to here is wavelength. If I consider the distance from here to here is wavelength. So it is not merely the straight distance between consecutive crests or consecutive troughs, but it is a straight distance between any two consecutive particles which are in phase. I think it must be clear to you with this model. And its SI unit is meter. Then wave velocity. It is the displacement of a wave per unit time. How much ever is the distance traveled by a wave in specific direction in unit time, which will be measured in meter per second. And you have also learned the relation between velocity, frequency and wavelength, that V is equal to frequency into wavelength. So what are the relation between these quantities? You know, F is the frequency, T is the time period. You have learned this relation even in the lower classes with respect to a pendulum. So F is equal to 1 upon T or T is equal to 1 upon F. The relation between them, velocity is the product of frequency and wavelength. And velocity in a given medium remains same. That means if the frequency increases, wavelength decreases. Which means ultrasonic waves which has higher frequency will have lower wavelength. And infrasonic waves which has lower frequency will have higher wavelength, but their product will remain the same. Since F is equal to 1 upon T, I can also write it V is equal to lambda upon T. Now, when the waves of same type are traveling in a medium, the velocity remains the same, which means that F into lambda product remains the same. So I can write down F1 lambda 1 for two waves traveling in the same medium of the same type. What do I mean by the same type? If F1 and lambda 1 is for light wave, I cannot take F2 and lambda 2 for sound waves. Both of them should be sound waves or both of them should be electromagnetic waves. Both of them should be of same type of waves. Okay, and in traveling in the same medium. If the first one is a sound wave and second one is a sound wave, but the first one is traveling in water and second one is traveling in air, I cannot equate this. I can equate this for same type of waves in the same medium. Since F is equal to 1 upon T, so F1 will be 1 upon T1, F2 will be 1 upon T2. So I can write down lambda 1 upon T1 equal to lambda 2 upon T2 equal to lambda 3 upon T3, and that is equal to constant velocity. When a wave enters from one medium to another, its frequency remains the same. So V is equal to F lambda. If I make F as a subject of the formula, it will give me V upon lambda. So that means when a wave enters from one medium to another medium, V upon lambda ratio will remain the same. So V1 upon lambda 1, V2 upon lambda 2, where 1, 2, 3 are the media. Here 1 and 2 are the waves. Here the same wave entering into the second medium. The velocity and wavelength of the wave in the first medium. Velocity of the wave in the second medium and the wavelength, the ratio between that, and this is the same wave in the third medium. Now, coming to the main part, what do you mean by natural frequency? Now, let us say that if I bang this table, so there are certain vibrations produced. Any surface when I bang, you can feel the vibrations. Now, when any body is disturbed once, okay, it vibrates with certain constant frequency. The body may stop vibrating again, even if I disturb, it will vibrate once, of course. It will vibrate with certain constant frequency, which depends on its size, shape, and structure. And this frequency is called as a natural frequency of a body. Now, in fact, afterwards, with the help of a simulation of a pendulum, I will explain you this exactly. I mean, the clarity will be better when I explain it with the help of a simulation. And obviously, the corresponding time period will be called as natural time period. So, when any body vibrate with constant frequency, when it is disturbed once, is called as a natural frequency, and the corresponding time period is called as natural time period. Now, what are free vibrations? Now, when a body vibrates without the influence of periodic force, obviously, please understand, at least force need to be applied once to transfer the energy, because without application of force, you cannot transfer the energy to the body. Without doing work, the energy cannot be transferred. So you have to apply the force once, but when I say periodic means continuous, there is no continuous force acting on the body. So when a body vibrates without the influence of periodic force, with constant frequency and amplitude, then these vibrations are called as free vibrations. Now, if a pendulum is suspended, you disturb it, it comes to rest after some time. Will you call them as free vibrations? No, because amplitude does not remain the same. But if this pendulum is made to vibrate in a frictionless medium such as vacuum, then in that case, I can call these vibrations as free vibrations. Now, vibrations of pendulum in vacuum is an example of free vibrations. Vibrations of a tuning fork in vacuum is an example of free vibrations, because there is no frictional resistance of a medium. When this pendulum is vibrating to and fro on either side, you'll find that the amplitude remains the same. Okay, so these vibrations are free vibrations. Now, during free vibrations, the body vibrates with the natural frequency. When a body vibrates freely, its frequency of vibration is natural frequency. Now, what will happen if there is a frictional resistance of the medium? If the frictional resistance of the medium causes the decrease in the amplitude, because of the friction, gradually the amplitude of vibration decreases. Then in that case, these vibrations are called as damped vibrations. Now, under normal circumstances, due to the frictional resistance of the medium, the damped vibration only decreases the amplitude. It does not affect frequency and time period unless and until there are different damping forces. Now, let us see this simulation. Now, this is a pendulum of certain length. I think I can change the length. Okay, I can change it to 0.6 meter. I am keeping the stopwatch on, and you will see that when it is oscillating, its period will be traced, time period will be traced. Now, I have set the length. I am going to allow it to vibrate freely. My frictional resistance of the medium is 0, which means that this pendulum is vibrating in a frictionless medium. You can imagine that it is vibrating in vacuum. Okay, now I am going to find out how much time does it take for 10 vibrations. So whatever time you get divided by 10 will give you time period. Now, when I am doing this, because of the human error, there could be slight change in the milliseconds, but the main seconds will remain the same. Now I am disturbing this pendulum. I am giving it certain amplitude. I am measuring the amplitude in terms of angle, which was 20. Now I am going to synchronize my count. When it comes at this point, I am going to count in the first case 0. And afterwards, you watch the vibrations. Every time the pendulum will touch these things, the amplitude will not change. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has taken 15.7. So if I divide it by 10, it will come nearly 1.57 seconds. Now if I stop this and again if I disturb, it will show more or less the same time period. Okay, 1.5 something. This milliseconds may change because of the human error. So I am going to disturb it again. And I am going to start the vibrations. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have seen that the time period almost remains 1.5. It remains the same. That means the frequency remains the same. The amplitude is also constant. Okay. So now what I'm going to do is that I am going to change the size of this pendulum. So you will find that the time period will also change. I'm going to change the length. So I'll change it to 0.8 now. And I am going to set this pendulum into oscillation. Let us take, even if I choose different amplitude, it won't make any difference because time period does not depend on the amplitude. I am going to start vibration, count the vibrations from 0 when it comes to this point. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now you see that the time period has changed because the size has changed. So natural frequency depends on the size. So I've changed the length, the time period of the pendulum has changed. Now let us introduce, now you know for this length the time period is nearly 1.8, okay, and the amplitude was the same. Now I am going to introduce the frictional resistance of the medium. There is some friction. Now when I disturb the pendulum, you will find that the amplitude will gradually decrease. I'm setting it to 0 again now. I'm going to count 10 vibrations. I'm starting the vibrations now. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There is slight 17.85 because I pressed slightly early. I could realize it. But it is very close to 1.8. Okay. So you will find that as the time period, as the frictional resistance of the medium is present, gradually amplitude decreases. And these vibrations are called as damped vibrations. I'm sure with the help of this simulation, it must be clear to you what are free vibrations and damped vibrations. Now let us go ahead with the forced vibrations. Now what do you mean by forced vibrations? Oh, sorry. Before that, the graphical representation of free and damped vibrations. If you are asked to represent graphically, you need to mark these points at equal distances. The students tend to randomly mark this. It is absolutely necessary to have the same amplitude up and down and these points at definite distances. You need not draw the graph, but you can mark them with the help of a ruler, say at a distance of 2 centimeters and write it as 0.1, 0.2, 0.3, that is sufficient. But if it is damped vibrations, gradually the distance will remain the same, but gradually the amplitude will decrease. So that is the graphical representation. Now coming to forced vibrations. Now when a body vibrates under the influence of periodic force, then the vibrations are called as forced vibrations. Now, example, vibrations produced in the board of guitar. When you pluck a guitar, the string vibrates, it transfers the vibrations into the board of the guitar. Very common example at your home also, when you start a mixer or when you start washing machine, in the surrounding floor or in the wall, you can feel the vibrations. Those vibrations are forced vibrations. Now, to understand this, okay, now the forced vibrations have two possible cases. Now, suppose there is a pendulum and I apply the force on this pendulum. Now, let us say the time period of this pendulum, we say 0.2 seconds, which means that the pendulum moves from A to C back to A in 0.2 seconds. Okay. Now, if I keep on applying force on this pendulum, continuously keep on hitting the pendulum, say after 0.1 second. Now, when the time period of the pendulum is 0.2 seconds, which means that 1 upon 0.2, that is 5 hertz is the frequency. So now if I keep on applying the force on the pendulum, say after every 0.1 second, then what will happen? After 0.1 second, you know that the pendulum is over here and it has tendency to vibrate. It has tendency to vibrate in this direction, and I'm hitting it in the opposite direction. And if I keep on hitting with this time period, what will happen? Sometimes the pendulum is moving towards A, I am hitting in the opposite direction, or sometimes the pendulum is moving towards C, I am hitting in the same direction. So sometimes my applied force will help the vibrations of the pendulum, but sometimes my applied force will oppose the vibrations of the pendulum. It will not constantly assist the vibrations of the pendulum. So it will disturb its amplitude and amplitude will become less. It will not vibrate with maximum amplitude. Under this condition, these vibrations are merely forced vibrations. But just imagine, I keep on applying force after every 0.2 seconds. That means after every 0.2 seconds, the pendulum goes over there, comes over here, I hit it. The pendulum goes over there, it comes over here, I hit it. That means the natural frequency of the pendulum and the frequency of the applied force. This is the natural time period. This is also the natural time period. So since the natural time period of the applied force is 0.2, which means that the frequency is 5 hertz. In 1 second, I am applying force 5 times. So since both of them match, you can imagine at no point of time, the force will be applied on the pendulum to oppose its vibration. All the time it will assist the vibration and gradually the amplitude of vibration increases. So this particular case of forced vibration is called as resonance. So forced vibrations have two cases. When the frequency of forced vibrations does not match natural frequency, they are just called as forced vibrations. During this, amplitude of vibration is never maximum. You will find that next time I will show you the videos in the next session, application of the pendulum. So you will find pendulum slightly oscillates, stops, again oscillates, stops, but it will never vibrate with maximum amplitude. When the frequency of the forced vibration matches the natural frequency and the amplitude of vibration increases, then this phenomenon is called as resonance. Now, to show this swing will give you exact idea of resonance. Now, if you observe this person, when is he pushing the child who's sitting on the swing? He is not applying force in between. Once he pushes, when the swing comes back to the extreme position back towards him, that time he is applying force. So that means he is matching the frequency of the applied force with the natural frequency of the swing, which depends on the length of this swing, which I showed it to you with the help of pendulum just now. So the frequency of the force vibration matches. Imagine if he steps forward and gives the push again, it will disturb the vibrations and the swing will not vibrate with maximum amplitude. It will disturb the amplitude as well as the vibrations. Now, I think students, we have learned today free vibrations. What are free vibrations? When the body executes vibrations without the influence of periodic force. Okay, these vibrations are called as free vibrations. Corresponding frequency of vibration is called as a natural frequency. Okay, and free vibrations are possible in vacuum, in a frictionless medium. We have seen the example of that also. During free vibrations, the body vibrates with natural frequency. Corresponding time period is natural time period. Then what are damped vibrations? Due to frictional resistance of the medium, when the amplitude decreases, then these vibrations are called as damped vibrations. What are forced vibrations? Forced vibrations, when a body vibrates under the influence of periodic force, then the vibrations are called as forced vibrations. And under this, there are two possibilities. Either the frequency of the force vibration does not match. So that time, as I explained you before, sometimes the applied force assist vibrations, sometimes applied force resist vibrations. Okay, and they are just called as force vibration, and amplitude is never maximum. It increases, decreases, increases, decreases, but it is never maximum. And when the frequency of the applied force matches the natural frequency, the body begins to vibrate with increased amplitude, because every time the applied force helps the amplitude to increase. It never opposes the vibrations of the body. Now, let us go to the assignment. Please write down these questions for the assignment. What is meant by natural frequency of vibrations of a body? Name one factor on which it depends. I am repeating. What is meant by natural frequency of vibrations of a body? Name one factor on which it depends. I hope you have finished writing this. I'm going to the next. You can draw this diagram, rough sketch. The above diagram shows two pendulums A and B tied to a stretched flexible string. It is observed that when A is disturbed once, after some time both are seen vibrating. Name the vibrations of pendulum A and vibrations of pendulum B. I think I'm going to the next question now. You must have finished writing this. A tuning fork is struck on a rubber pad, and the stem of the tuning fork is touched to a table surface. That means the vibrating tuning fork. The table surface starts vibrating. What is the difference in the vibrations of the tuning fork and the vibrations produced in the table? I am going to the next question. Draw a displacement time graph representing first one free vibrations and second damped vibrations. I think you have finished writing this. I am going to the next question. In what way does the medium affect the amplitude of natural vibrations of a body? I repeat, in what way does the medium affect the amplitude of natural vibrations of a body? I think let's go to your question answer round. What is meant by free vibrations of a body? Now, when a body is disturbed only once and left on its own to vibrate, the frequency of vibrations of a body is called as, or these vibrations are called as free vibrations. When a body is disturbed once and allowed to oscillate on its own or vibrate on its own, these vibrations are called as free vibrations. What is the name of the frequency of free vibrations? The frequency of free vibrations is called as natural frequency. If the time period of vibrating body is 2 seconds, what is the natural frequency of the body? I think it's better if I show this by working. The time period of vibrating body is 2 seconds. So time period is equal to 0.2 seconds. So we know that frequency is equal to 1 upon time period. So therefore it is 1 upon 0.2. So when I shift the decimal, I can make this as 10. So 2 5s are 2 1s are 2 5s are. So I will get it as 5 hertz is the natural frequency of the body. Define frequency of a sound wave. Here, children, I want to make you aware what common mistake the students make. Now, first I will tell you the correct answer and then I will tell you what mistake the students make. Now, sorry. The number of vibrations completed by medium particle of a wave in unit time is the frequency of sound wave. Very often the student, while writing down, write it as the number of vibrations completed by a wave. Now, a wave is produced due to vibrations of the particles. I've explained it to you before just now. So there is no meaning if you say that the number of vibrations completed by a wave. It is the number of vibrations completed by the particles of the medium or by wave particle in unit time is frequency. Name the vibrations produced in the body of a moving car. Now, when the car is moving, because of the engine, there is a block piston which is moving to and fro that causes vibrations, and it transfers these vibrations to the body of the car. So, the vibrations which are produced in the body of the car will be called as forced vibrations. They are forced vibrations. Similar to the example which I gave you before, that when a mixer is started, what are the vibrations in the surrounding platform? What is the difference between supersonic and ultrasonic sound? Now, supersonic means, actually it is not supersonic sound. The difference between supersonic and ultrasonic is, ultrasonic is the sound having frequency more than 20,000 hertz. And any body moving at a speed more than the speed of sound in air is called as body having supersonic speed. So supersonic means speed more than speed of sound, and ultrasonic means, may I have the question again? Ultrasonic means having frequency more than 20,000 hertz. Does sound propagate in the form of particle nature or wave nature? Now, sound is that means it's a mechanical wave. So it always travels in the particle nature in the form of wave. But particle nature means if you're talking about the particular theory of light, it doesn't. It has a wave nature, but it is a mechanical wave. How is frequency dependent on the wavelength of the sound? Now, frequency and wavelength are inversely proportional to each other. If the frequency increases, the wavelength decreases. The frequency decreases, the wavelength increases. Define resonance. Now, resonance is a particular case of forced vibration where the frequency of the applied force matches the natural frequency of the body and the amplitude of vibration increases. So this is resonance, or when the body vibrates under the greater amplitude, when the frequency of the force vibration matches the natural frequency, is called as resonance. What is inertia? Now, inertia is a tendency of a body to be in its state. Now, it is always measured in terms of mass. Now, because of inertia, when a wave propagates in the medium, it gives a delayed reaction. That means all the particles of the wave do not receive energy at the same time. When the energy is received by the first particle, then it transfers, because it has mass, so it transfers the energy to the next particle, and there is a time lag between the two, and therefore you get this wave form or wave nature. So inertia is basically tendency to be in its state, which is measured in terms of mass. Yeah. What is the relation between frequency and amplitude of a wave? There is no correlation between frequency and amplitude. You can have same frequency with more amplitude or less amplitude. You can have less frequency with more amplitude and less amplitude. There is no correlation between frequency and amplitude. Does sound travel in uniform motion? Yes, in a given medium, sound travels in uniform motion. What is the difference between damped and forced vibration? Now, damped vibrations are normally considered as the vibrations which are caused under the frictional resistance of the medium. So normally when damped vibration takes place, amplitude gradually decreases. There is no increase in the amplitude. But forced vibrations, the amplitude can decrease or increase, as we have talked about the resonance. So damped vibrations, yes, external force is there, but that's a frictional force which causes continuous decrease in the amplitude. At no point of time there is increase. But in forced vibration, there can be. Will the pendulum in vacuum keep on oscillating? Yes, ideally yes, but at the point of support, there is a friction. So because of that, after very long time, it may come to rest. What is crest and trough? I will show it to you with the help of this diagram. Now, can you see? So, all these points of maximum positive amplitude are called as crest, and these are called as trough. So you can say the maximum displacement, positive displacement during vibration is crest, and maximum negative displacement can be called as trough. What is the effect on the oscillations of a pendulum if the friction is increased? So if the friction is increased, the amplitude will decrease more rapidly. Amplitude will decrease faster. Body will lose energy. Body will lose energy. Which type of vibrations does a tuning fork have? Now, tuning fork will show damped vibrations unless and until it is vibrating in a frictionless medium. But in a medium, it will show damped vibrations. So damped. What are ultrasonic waves? So ultrasonic waves are the waves having frequency above 20,000 hertz. I think let us take this last question because time is running out. What is the speed of sound of frequency 800 hertz having wavelength 40 centimeter? I think I will have to show the working of this. Sir, could you please show the question? Question, sir. Now, frequency is given to be 800 hertz. Wavelength is 40 centimeter. To convert it into meter, I have to divide by 100. So it is 0.4 meters. So therefore, I know velocity is f into lambda. So frequency is 800 into wavelength is 0.4. I get rid of this decimal, cancel this 0. 8 4s are 32, and one more 0. Meters per second is the speed of sound. Thank you everyone for listening, and we will continue with the second part of it with the application, which has more interesting videos and some of the experiments which I'll be showing it live. So thank you everyone. Thank you to the council for providing me this platform to teach the students.